We're going to continue in factoring. This time we're going to look at special binomials, or two terms. The first one is the difference of squares. You might recall that previously if we had something like x plus 3 times x minus 3, when we multiplied it out, this middle term canceled with this other middle term, and it left us with something like this, where the first term and the second term are both perfect squares. We're going to use this to our benefit, and we're going to work it backwards. If I'm given something like 4x squared minus 1, I can go off of what we previously reviewed and know that it factors into two conjugates. The square root of 4x squared is 2x, and the square root of 1 is 1. And if one of these is positive and the other one is a negative, the middle terms will cancel. Differences of squares always factor into two conjugate pairs. Okay. So when we have two terms, the first thing we should always look for whenever factoring is the greatest common factor. But after that, if it's two terms, we want to make sure that we're asking ourselves, can I square root the first term? If I can, what is it? Can I square root the second term? If I can, I know it's a difference of two squares, and I also now know what each factor will look like. 5a plus 3b, 5a minus 3b, as in this example. But again, like I said, you want to make sure that you look at the problem. Do you have a greatest common factor? If you have a greatest common factor, it will look a little different. All right, next example. What did we put here? Minus 2. Okay. So 162 is even, so we know it's divisible by 2. And there's the 2. So we're going to pull out a 2. 2 goes into 162 81 times. And it goes into itself once. Now you might be looking at this x to the 4th and saying, is that a perfect square? Remember your exponent rules. Square root of 81 is 9. And the square root of x to the 4th, if you square a square, you get 4. We multiply these in this situation. So my first term is a perfect square. My second term is a perfect square. So these will fit that pattern. Don't forget the 2 that you've already factored out front. Your greatest common factor is a factor. It needs to follow the problem. This brings us to another situation. I've already factored it once, but do either of my answers fit the pattern again? This one does. The square root of 9x squared is 3x. The square root of 1 is 1. So that is doable. You might say these two are perfect squares. Do these also factor? No. That's a plus. There's no way to get, in two terms, that one to factor. It's prime if there's no greatest common factor, which there isn't because we already pulled it out. So this nice little compact problem we started with, once factored, is that long. This long answer. Let's see what else. I covered everything. You might say, well, that's nice, we have squares. Will it work with cubes? It's similar, but not quite the same. cubes have a pattern also. We might have an x plus a y, or we might have something minus. Sum of cubes and difference of cubes are both factorable. I'm going to write the pattern out for you first. Ask yourself, can I take the cube root? If you can take the cube root, that's going to go in your first set of your first factor, x plus y. Your next factor, as you can see, we need a cube. So I'm going to need to multiply an x times an x squared. I'm going to give myself room. I also know that I need a y cubed, so I need a y squared. It's this middle that's a little bit different. This is 3 terms, a binomial times a trinomial. And you get that middle one by changing the sign. This sign change from here to here is what makes all the middle terms cancel. Then we're going to multiply the cube root of the first times the cube root of the last. So xy, and this last one's always a plus. It's going to be the same for the minus. The cube roots go in with the same sign. You get the first term squared, change the sign, first root, cube root, times the second cube root, and then always plus the last one squared. Now that we have the pattern, let's practice it on a couple problems. Y cubed minus 27. So first, ask yourself, is there a greatest common factor? Not in this case. Since it's 2 terms, it doesn't fit a pattern of difference of squares, because that's not a square, nor is y cubed. So we're going to see if it fits into something cubed, either plus or minus something else cubed. And if you don't know if 27 is a perfect cube, you can prime factor it. 9 times 3 is 27, but 9 is not finished. So we have 3 times 3 times 3. So 27 is a perfect cube, and it fits the pattern. So we're going to put the cube roots with the same sign in the first factor. Then to start the second factor, we're going to square this first one. We're going to multiply this times this, but change the sign. Then we're going to square this last one. This is factored. Okay. Let's practice one more. 54a cubed minus 16b cubed. Obviously, again, we're not looking for squares because these are cubed. But first is always the greatest common factor. 54 and 16 both have a 2 in them. So let's factor it out. Yep, 27. A cubed minus 8b cubed. So neither 54 nor 16 was a perfect cube. By pulling out the greatest common factor, we have a 27, which earlier we saw was a perfect cube. What about 8? Well, if you remember, 8 is 4 times 2, and 4 is 2 times 2. We can see that 8 is 2 cubed. So it fits the pattern. The 2 is still out here. So we're going to finish up bringing our greatest common factor of 2 along. Then we're going to put our first cube root, keep the sign, our second cube root, and then we're going to square this first cube root, and don't forget to square the number. So 3a times 3a is 9a squared. Change your sign, multiply the 2 cube roots, so 2b times 3a is 6ab. Then square the last term, and don't forget again to square the coefficient also. That is this square. So to sum up, when we're factoring 2-term or binomial expressions, we have first the greatest common factor, which is always first, but then we had two special things to look for. We had the difference of squares, which factored a squared minus b squared, factored into two conjugate pairs, one with the plus sign and one with the subtraction. And then we also had the sum or difference of two cubes. And those patterns, two formulas, one pattern. A cubed plus b cubed factored into the cube roots with the same sign. First root squared, change the sign, cube roots times each other, and then always the last cube root squared. And if we started out with a cubed minus b cubed, we took the cube roots and kept the sign, squared the first cube root, changed the sign, multiplied the two cube roots together, and added the square of the last cube root. And there you have the two different things you would look for if you have two terms to see if it's factorable.